Okay, hi everybody. I'm Luca Ceresoli, and I'll talk about how Linux can run on the ZynqMP processor by Xilinx, especially in the ways that it differs from other system on chips. I work as an embedded Linux engineer at IIM Sportline, designing the next generation data loggers, dashboards, and action cameras for racing. I also love open source, of course, and I contribute to some projects, including Buildroot. Okay, so I will first give you a brief introduction about the chip itself, and then proceed to which development tools are available, how Linux can use your FPGA design, and how to boot this thing. And then there are a few shorter sections about using the GPU and the video codec unit. Okay, so basically the ZynqMP is a so-called SoC plus FPGA, so it is a system on chip, pretty much like many others, but it also had a piece of FPGA which is directly connected to the processor on chip, which makes it very efficient with respect to other architectures where the FPGA is connected externally, or the CPU is synthesized on the FPGA itself. If you are new to the topic, there is a good introduction by Marek Vajut. This talk is an overview of the topic, which is quite good. Okay, basically the two main vendors for this kind of thing are Xilinx and Altera, which is now Intel. And I'll be talking about the current second generation by Xilinx, which is the Zynq Ultra Scale Plus MP SoC, but people call it ZynqMP because it's shorter. There is a previous family generation of SoCs, which is a Zynq 7000, which is now pretty much well established. Intel has a pretty similar set of two generations of processors, but I don't know much about them. Okay, this is the block diagram of the system on chip. As you can see, it has, well, in its most complete versions, it has quad-core ARM64 processor, A53, 2 real-time cores. It also has the usual long list of peripherals for system on chips. Most of them are connected to a low-power interconnect. A few of the faster peripherals are on the full power interconnects. Okay, then there is also a GPU in some versions. There is, of course, a DRAM controller. There are two specialized units, the CSU and the PMU, that are involved in booting, so I will talk about them later. It also has a video codec unit, which is a video encoder and decoder in hardware, and some other very fast peripherals that I'm not talking about. And then there is, of course, the FPGA, which makes this design quite peculiar. Okay, so to develop on this kind of on processor, of course, first of all, you need documentation. There is a lot of documentation, generally quite good by Xilinx. It's accessible on that pretty long URL on their website. There you find like a few dozen documents of general interest about the platform, and then there is much more. Okay, then starting bottom up, you design your FPGA. This is not the subject of this talk, but anyway, just briefly, the tool that Xilinx provides for this is the Vivado design suite, which includes Vivado itself, which is the thing you use to design FPGA down to the bit stream, which gets downloaded into FPGA. And then there is the XSDK, Xilinx SDK, which is an Eclipse IDE to build firmware, bare metal software for the Xilinx processors. All of this runs quite okay in Linux, and there is also a zero-cost version. It's all license-based, so it's not really completely free, but the zero-cost version has most of the features, but not the most advanced ones. Okay, so it's quite useful. It does a lot of things. However, it is closed source. It is a very huge software to install. You have to have a pretty powerful computer to use it. It also has some bugs and annoyances that people complain about. but of course it's closed source, so you can't do much about that. But it's generally a good product, but you might wonder whether you can use some open source alternative. You're not that lucky because today it is not possible to use a fully open source toolchain for this kind of FPGA. Although there is a reverse engineering effort in progress. It's called the SimiFlow project, and it's in quite an early stage for the Zynq 7000 platform. So for ZynqMP, it's probably very soon now to expect something, but it's good that this thing exists. Okay, here is an interesting link on other reasons why you might want an open source toolchain. Okay, when you have your FPGA working, you need to build the software on top of it. And of course, the two main pillars of a BSP to support the processor are Linux and U-boot. And okay, about U-boot, Xilinx is quite active in working on mainline U-boot to support their own processors, which is very good. I think it's supposed to be ready to boot ZynqMP processors in U-boot mainline, although I haven't tested that because it doesn't support the board I have. But there is also some additional development that you can find in the Xilinx GitHub repo. They have their own U-boot fork with things that are not yet in mainline, so you may want to look at that if you need something, a board or a feature that is not yet in the mainline. Okay, the other big piece is, of course, the Linux kernel, and the situation is quite similar, so Xilinx is contributing to that as well. Although I think they are a lot more behind, so I think it's quite incomplete so far. So you might probably want to have a look at the Xilinx fork on GitHub. It is the current branch from Xilinx has started like 1 year ago, so it's diverging a lot from mainline. But from time to time, they start a new branch, somewhat like once per year probably, not official. So there might be a new branch starting, being published soon from a recent kernel. The one that's now in use is a branch from kernel 4.9. Okay, and on the Xilinx branches, you can find both development for the hard silicon features that are specific to ZynqMP and to the IP blocks that you can put in FPGA and that are new in the ZynqMP that were not existing before, especially related to video processing. Okay, and finally you need to build the whole system. And in this respect, you have to make a choice about the workflow that you want to use, because there are at least two main possibilities. I've called them the Xilinx workflow and the community workflow. The first is the one that Xilinx supports and documents in their own reference designs. And the second is developed by the community with some support by Xilinx also. And it is closer to how other open source development works in other vendor system on chips. Of course, you can somewhat mix and change on this, but these are the two that are in most common use as far as I know. Right, the Xilinx workflow involves, of course, using Vivado and XSDK for the FPGA and the bootloaders and the low-level stuff. And then they use PetaLinux as a build system, which is a Xilinx-specific build system. It used to be a build system on its own, different from other things. Nowadays, it uses Yocto internally, so it got a bit more standard. Although, if you use PetaLinux directly, you don't see Yocto working, but it's there somewhere in some of its subdirectories. So you can have a look at how it builds things and which recipes it used. It uses actually those 3 layers mainly. So in case you want to have a look, they are all on GitHub anyway. And the other workflow, the community workflow, also involves using Vivado because it's currently the only tool that you can use to design the FPGA, and also a little bit of XSDK. I will talk about that later. And then there is one layer, the Meta Xilinx BSP layer, which is developed quite in line with the standards for a Yocto project, and as well as a general BSP for any system on chip. All right, and but this does not support yet all of the features, but it's already quite complete now. Okay, a couple other useful resources. There is the Meta Xilinx mailing list, which is mostly to discuss the Xilinx related layers, but it is also a place for general discussion about the usage of Linux on this SoC, on Xilinx hardware in general. So it's useful for many users. It's low traffic, so you can follow it easily. And also there is this layer, Meta Topic, which is just support boards made by a manufacturer called Topic Embedded, but it has some useful code that I used that is not found on other layers. Okay, there is no currently support for the ZynqMP in build root, but it's work in progress. There is a first patch set on the mailing list that had basic support from one board, and it will evolve to probably support it in the next few weeks or months. Okay, let's see now when you design your FPGA, how you can run it on Linux. The very interesting thing that I found very cool about this kind of chip is that you can basically design your own system on chip. That's because the FPGA is connected to the CPU via ARM64 buses. ARM64 is part of the AMBA specification by ARM, so it's the same kind of buses that is used inside the system on chip to connect the processor to the peripherals, and so it follows the same standard. You can access the registers in an IP block in FPGA just like you access the registers on an IP block in Silicon, and so it actually becomes like a system on chip that you design in part. Okay, the steps when using Vivado are mainly three: IP integration, address editor, and constraints. The first step, IP integration, it takes place in this window, the block design editor. You can't read that, that's okay. It's blocks connected by lines, so it's basically oversimplifying, but that's an electronic circuit. Each of these blocks gets synthesized into FPGA, and with some exceptions, the block one here with Zynq Ultrascale written on top of it does actually represent everything that is on the chip outside the FPGA. So it's there just to, because this view is FPGA centric. So that is there because you can double click on it and customize it. So you can customize how you want the hard silicon part to work. You can configure the PLLs, the power domains, the various peripherals, buses, and so on. And this results in a configuration file that gets saved, which actually sets a long list of registers into the various peripherals. If you double click on other blocks, such as, for example, a GPIO block, you can customize that one as well. In this case, it will change what will be synthesized in the FPGA. For example, you can say for this GPIO block, you only want three pins, not 32, because you need only 3, so you optimize usage of your FPGA. You want only inputs, and you cannot set output because you don't care, and you want to have an interrupt. Where is it? Oh, here. You want an interrupt line. So in this case, you will have a customized hardware. And when you synthesize that in FPGA, you need to put it on Linux. So there is a wiki page by Xilinx which lists all of the devices that can be present either in Silicon or in FPGA, and how to use them. So it points to which is the Linux driver, and there's some documentation of it. And in the Linux kernel, the device tree bindings are documented. So you can write your own device tree snippet to support this block, and it's nothing but a GPIO controller with its own compatible string that you get from the documentation. But you also have to say sometimes several parameters to tell to Linux how the hardware has been synthesized. So you have to tell it, it has 3 pins, they are all inputs, it has interrupts, or they are all outputs, and so on. Otherwise, the operating system will try to access registers that are not implemented, or generally to use features that are not there, and this will result in crashes. So it's very important that you keep in sync your FPGA bit stream with your device tree. It's very easy to like update one and not the other, and then everything crashes, so you have to pay a lot of attention to this. Okay, so interrupts are managed this way. The non-FPGA part can have up to 2 interrupt ports, each of 8-bit, and you can connect it. This line here comes from the GPIO block you've seen before, and so it will end up in one of these things here, and this entering the hard silicon part, and this is connected to the GIC, so the main interrupt controller in the ARM core. And so this is how you do it in Vivado, and you configure it in Linux in a very standard way. So you have interrupt parent is the GIC, unless you have an additional interrupt controller outside, of course. And you have interrupts, which takes 3 parameters, so it's the type of interrupt, but the most important is this one, which is the interrupt number. To know which is the interrupt number, you have to add your offset here to the base number, which is somewhat hard to find. You have to look here and there to find it. But luckily there is a file that has defines for them. So I think this is 96 or so. Unfortunately, that define file, that the DTSH file that defines this one is not in the kernel sources. I found it on this other repository here, so I copied it immediately in my kernel, and it's very useful. Okay, next step in Vivado is the address editor. Whenever you add a block that is accessible via an interconnect, it will add a mapping in the address map for that block. So this is all done automatically. And for the GPIO block, it will be accessible at address A00 blah, blah, blah. This is something that you can change if you want. And then this is the number that you have to put in device tree. So you, in your reg keyword, you have to put this address here and the width, which is in most cases 64 bits. And that's it. So that gets very standard. Again, you have to keep them in sync. Your bit stream with your device tree must be in sync, or everything can happen. The third step is define the constraints for each of the nets, basically the lines in your FPGA design that go outside the chip. You have to define to which pin they map, the I/O standard, whether they have a pull up or pull down, the similar things. But this is not, this doesn't affect the Linux part because it is not related to the software, but rather to the outside of the chip. So no visible impact here on the kernel. Okay, that's all for the Linux configuration. It's pretty standard if you pay attention to keeping things in sync. And the next big step is you have to boot it. Well, actually, it's the previous step, but I put it in this place. Okay, back at the good old times with simpler system chips, you just had to load an SPL from storage to internal RAM that initialized RAM and loaded the big bootloader, which loaded the kernel. In ARM64, it's a lot more complex, of course. And one of the items that are involved is the platform management unit, the PMU thing, which is here, which is a processor that is responsible to do all power gating and clock gating. So it is very, very important for the system to run. You cannot boot without its intervention because it has to enable the devices you need. This design is somewhat similar to many other ARM64 boards. It's rather complex, but so you have to handle this. It's mandatory. And okay, another unit involved is the CSU, the configuration and security unit, I think. And so, first about the PMU. The PMU is actually a microblaze processor, so it's a small microcontroller basically, which can executes a firmware that you can reprogram. But in the practice, you must reprogram it if you want to boot, because both U-boot and Linux require a PMU firmware that is more recent than the one in some silicons, and so you have to reprogram that. Luckily, the source code has been made public by Xilinx with it's actually a permissive license, but with the restriction to execute only on Xilinx hardware. But anyway, the sources are there, you can work on them. And there is a recipe in the Meta Xilinx BSP master branch to build it. In order to build it, it first builds an entire microblaze toolchain with ULib. So it will end up in a firmware built for you. Okay, and the PMU firmware does not run on its own. It also needs a configuration object. It basically tells which master owns which slave, where masters are more or less the CPUs and the slaves are the peripherals. So that's just to avoid that both the Cortex A53 and the R5 or another processor synthesized in FPGA request the same peripheral, and this wouldn't work, of course. This configuration depends on how you configure things in Vivado, in the big window where you configure the hard silicon block. So there's a configuration file generated for that. Another big component you need for booting is ARM trusted firmware. You need it on, I think, every ARM64 architecture. And what it does is it answers to U-boot or the kernel or whatever is in the less privileged execution level. It replies to SMC calls, which SMC is an ARM standard. And these calls allow, for example, to enable devices and so on. But actually, ARM trusted firmware does not do the job, really, but forward this request to the PMU using Xilinx specific API. So you need both of them. And when, for example, U-boot or the kernel tries to enable a device, it will ask ATF, which in turn asks to PMU, and then the device gets enabled. Okay, there are two workflows, as I mentioned earlier, and there are two boot flows also. So if you're using the Xilinx workflow, you are guided to use this boot flow, where there are mainly three actors: the PMU, the CSU, and one of the processors. For example, the A53, but it could be the R5 as well. At power up, the PMU wakes up, and all it does is wake up the CSU. The CSU loads the first stage bootloader, is a Xilinx specific bootloader, into memory to be executed by the A53 processor, for example. And it also loads the PMU firmware inside the PMU. So it is where the PMU firmware gets updated during boot. All right. Then the FSBL loads from the boot medium the configuration object and send it to the PMU, and then ATF and U-boot. So this way, U-boot can really start and go through ATF and PMU to do all of its stuff. So it's quite complex. Okay, and in order to build the pieces, you have to go through this thing. You start from Vivado with your HDL design, your FPGA design, and it produces an HDF file, which means hardware description file, which in turn you use to open the Xilinx SDK, and based on how you configure the hardware, it has wizards to produce a PMU firmware, a first stage bootloader, each with its own BSP. It's all done via wizard, so it's very easy. And in the end, they will produce the two binaries for the PMU firmware and the FSBL. Also, the FSBL BSP is the place where this file, pm configuration object.c, will be created. It is the configuration object to be fed to the PMU. And so, as you can see, it's in the FSBL. So it's the FSBL that owns this configuration. All right. Then Peta Linux, actually via internal IOP rules, will build ARM trusted firmware and U-boot. And all of this, along with the bit stream for the FPGA, is fed to the bootgen tool, which will produce the boot.bin file. Boot.bin is the big file with all of the things that happen in boot before the Linux kernel, basically. And it is put on your boot media, for example, the SD card, and then the hardware, the boot ROM loader, which is executed by the CSU, will load from the boot bin only PMU firmware and FSBL. And then FSBL will open the file again and extract all of the rest to put them in memory or in FPGA. So that's the build flow with the Xilinx workflow. This has some advantages. It's supported, of course. The Xilinx tools make it easy with wizards and clicks. And also the FSBL code is very simple. It's simple to understand how it works. So if you want to understand what's going on. But on the other hand, it's not optimized, so it's super slow. For example, to load a relatively small FPGA, it takes like 3 seconds, which could be optimized a lot. Also, the Xilinx tools are a pretty heavy requirement, especially if you have continuous integration, you have to install them, and then they are hard to automate. So it is a little bit cumbersome to use in some cases. And also the proprietary bootgen tool is needed to generate the boot bin with all of this stuff. And finally, this flow is completely different from other build flows that you probably used on other vendor SOCs. So let's see what's the alternative that the community has come up with. And this one is, the core of this alternative is that we have to replace the first stage bootloader with something else, because the first stage bootloaders need a boot bin produced with the Xilinx specific tools, and so we want to replace FSBL for performance and for this reason. The obvious replacement is U-boot SPL, which does a very similar thing. But there are a few obstacles to this. First is that U-boot SPL cannot load the FPGA like the FSBL does. This is not an issue, however, because U-boot can load it, and it's also a lot faster than the FSBL. It's about 10 times faster because it's optimized. The second issue is that the U-boot FSBL loads U-boot, not ARM trusted firmware. So various architectures have various ways to achieve that. And in this case, there's a trick to achieve that. And finally, U-boot SPL cannot load the PMU firmware configuration object. So we'll get to the second and third point. Now, okay, to load ARM trusted firmware, the thing is, U-boot needs ATF, but so SPL must load both for U-boot to be able to run. And what happens is there is a trick to do this, which is in all the ZynqMP devconfigs, Falcon mode is enabled in SPL Falcon mode. This is a mode which is meant to achieve a higher boot speed than with regular U-boot. So what it does is SPL loads directly the kernel and the device tree in RAM and jumps to the kernel, completely bypassing U-boot to speed up the boot. But in this case, it is configured in such a way that the DTB image is called uboot.bin, and the kernel image is called ARM trusted firmware uboot.ub. So it thinks it's loading kernel plus DTB, but in the practice, it is loading uboot and ATF. So this approach works. This approach works, but you lose the possibility to use Falcon mode to really speed up the boot, because you've already hijacked it for something else. And okay, it's a bit of a hack, but at least it solved for us one of the problems. The other big problem is the configuration object. Configuration object must be loaded into the PMU firmware for it to work. but there is no code in SPL to do it. First, because nobody wrote it. Second, because of license conflicts. And so what happens is there is workaround. It is the best workaround that I know of at the moment, which is you take the PMU configuration object as produced by XSDK and link it directly into the PMU firmware, and then modify the PMU firmware to load it directly at startup. So it's hard-coded inside the PMU firmware. It's very simple. It comes from the metatopic layer that I mentioned before. It's not in mainline, not at the moment at least. I mean, not in the mainline with Xilinx BSP layer. It might be in the future. Okay, since understanding how all of these things was a bit complex and took a lot of time, I wrote a very trivial script that does the very minimum needed. It's in this repository. It does only three things: take cross-tool-ng to build a microbracetool chain, patch the PMU firmware sources, and build it. So it's easy to understand how the PMU firmware gets built, and it allows to use it without having to set up all of the Yocto machinery and rules to do it. So this approach works, which is good. On the other hand, it forces you to rebuild the PMU firmware every time you change your configuration in the core things. But anyway, you would have to rebuild the FSBL with the Xilinx workflow, so it's not very much different. Okay, so the boot sequence with the community workflow becomes this one. It is very similar to the other one, but the differences are SPL is loaded instead of the FSBL. So it's just another piece of code doing similar things. And the configuration object is not loaded by the SPL. It's hard-coded directly in the PMU firmware. The rest is all identical. Okay, but that's not all. We also need something else because, well, what you do in the in Vivado, you configure lots of devices and in all of this hard silicon part, and that results not only in the PMU firmware configuration object, but also in a file that is called psu init.gpl. Well, two files actually. There is .ca.h, and these need to be applied. It's basically a long list of register settings, so it sets a bunch of register to set PMUXes, PLL speeds, and the SD-RAM controller, and so on. This file can be obtained this way. So when you've done your design with Vivado, you can just do file export hardware. It will create the HDF file, which is actually a zip file. You extract it, and you get these two files. You put them in the U-boot sources in this directory. You will also have to make sure that those are built and not the other ones that U-boot has for some boards. And so that's it. When you've done with that, you have a U-boot that at boot will set all of those registers, and they will work. So the annoying part of it is that you have to launch the whole XSDK manually to produce a file just to obtain a single .c file. But the rest of the build process is well, maybe a little simpler. So it starts in the same way with Vivado producing the HDF file, and from that you can launch the XSDK, which you only use to launch the wizard, produce the FSBL BSP, and take the PM configuration object.c file. .c is missing, okay. From there, and that's it. Then you can throw away everything produced by XSDK. And the build process is entirely done by Yocto in this case, and it will be the quite standard ARM-trusted firmware. And U-boot, actually, it will build the PMU firmware along with its microbracetool chain, which links the PMU configuration object. And finally, the U-boot rules can produce of course, the U-boot proper, the SPL, and then they can produce a minimal boot.bin that only contains the SPL, and which is the the boot SPL and the PMU firmware itself. It doesn't contain all of the other pieces, and it doesn't do fancy features just like encryption and similar, so it's very minimal to this use case. In the end, you have just to put on your boot medium all of those files, because the other files are accessed by SPL. And that's it. So in this way, you can have a complete build which boots and works. It is one of the two main approaches. Okay. So that's it for booting. The next chapter is about the GPU. This system on chip has a GPU, which is very interesting, makes it very, very interesting. But the CPU is an ARM64 which is very sad because it has very bad support. I think it's likely the worst one in terms of software support. That's because it requires a binary blob, which makes things always a little bit complex and annoying. Basically, that's the only option, although there are two open source alternatives. One is the Lima driver, the reverse engineering project that has done a lot of the reverse engineering work, but has never reached real usability for complete projects and is now abandoned, I think. The other is the Mesa Lima project. It is quite a new project, started, I think, last year. And it's advancing not super fast, but steadily. And so it may be that at some point we have an open source driver for this GPU. Although at the moment I think it's ready just for do some simple rendering, not yet ready for complex applications. So let's see how you do things in the only possible way. So you have to use two components. There's a kernel driver, which is GPL, but it's not in mainline. One of the issues with this driver is it does not much. Actually, all of the real work is in the user space library. All the interesting stuff is done in the user space library, which is the binary blob that you have to use, and which implements the OpenGL ES APIs. So every other application is based on top of that. Also, this library is SOC specific, so you cannot reuse the library from other processors. So you have to use the one from Xilinx. To build these two components, well, the kernel module is fairly simple. There is a Yocto recipe on the Meta Xilinx DSP, which just downloads the sources for ARM and applies 10 patches, and then it builds just fine. I haven't looked into detail into it because it worked at the first attempt. The other part is the user space library, which is more complex. First of all, you have to find it. It's not in the main master branch for Meta Xilinx BSP. It is only in the Xilinx fork, which is on GitHub. So if you want to stay on the master branch working on that, you can just take the recipe from the most recent is the Rail V 2017.4 layer. You take the recipe from there, copy it in your own layer, and that's okay. It should work without any modifications. Now that you have your recipe, you run it, and it fails because it cannot download the sources. In fact, the URL to download the sources is from this domain, which is not accessible. It appears to be an internal repository for Xilinx, so you cannot download from that. So you go into the documentation, and there is a README file in the along with the recipe, and it tells you have to register on the Xilinx website, download the tarball, and open the tarball. There is some instructions and a second tarball, and then you have to extract the second tarball, which contains the third tarball, and yeah. No, that's all. There are only 3. We are almost finished. Then in the third tarball, when you extract it looked like a bare Git repo, and in fact it is. It is basically the thing that bitbake downloads in the download directory. It probably has been taken as is, put in a tarball, in a few tarballs, and then you have to put it in some random directory that you want and point source mirror URL in your local conf to this path, so that Yocto will find it as if it had downloaded it, and then things will work. So a slight simplification of this, well, I basically wrote a stupid script to do all of these steps because you have to redo it whenever you want to upgrade the library or whenever you want to bootstrap a new development machine. But I also chose to extract it in the main download dir for bitbake, so at least I can skip the last step and leave source mirror URL for what it's meant for. When you're done with that, you can use it in two ways because there are actually two different libraries. One is to use with FPDev, with good old frame buffer, and the other with X11. Okay, the frame buffer version actually works for normal needs of many embedded systems, like running a Qt or QML application on a single screen. It works, but forget multi-screen, it doesn't work. Apparently there is /dev/fb0 hard-coded in the library, so you cannot use more than one screen. So we tried X11, the X11 version, but we couldn't make multi-screen work with that one as well. Not sure why exactly, but QML with the software renderer works fine with multi-screen, while the accelerated one does not work. So I don't know exactly about that, but that's it. At least waiting for an open source alternative. And that's all for the GPU. And let's go to the video codec unit. This is a little better in terms of support, luckily. So what happens here is there is this video codec unit, which is an H.264 and H.265 in hardware. It's able to do like 4K at 60 FPS, so it's quite powerful. The interesting thing, it is not connected to an interconnect. It is floating in the middle of the FPGA, so you have to wire it inside the FPGA to use it, which I think makes it a little bit more flexible. Well, anyway, this is not a big deal. It's quite fast to do. And this is the whole stack to use it. From starting bottom up, there's the VCU itself, which needs a firmware, which is a binary blob from Xilinx. Then you have a kernel driver, you have a user space library, and an implementation layer for OpenMax. All of these three are provided by Xilinx with sources with the same license, which is permissive but restricted to Xilinx hardware. Okay, and then, well, OpenMax, as far as I know, is implementing APIs to interface to a codec. And so you can use it directly probably, but I think the most common usage is to use GStreamer. GStreamer as an OpenMax plugin, so you can just put an OpenMax H.264 encoder in your GStreamer pipeline. Okay, so to instantiate the VCU, you have to put a block in Vivado, just like the ZynqMP block. It's not really being synthesized in FPGA, but it represents how it should be connected to the rest of the world. And then you have to set up a device tree entry in Linux, which is standard, nothing special here. Okay, and then you have to set up all of the software. All the software is only in the Metapeta Linux layer, not in the Meta Xilinx BSP layer, which is a layer that you are not supposed to use with the community workflow. So I tried to use this layer just to have the VCU support, and I've lost a few days in beating my head. And after all, I understood it was better not to do it. The reason is that well, I'm using Yocto 2.4, which ships GStreamer 1.12, while Metapeta Linux has BB appends to change that to GStreamer 1.8. but then it tries to apply patches that it does not ship, so it expects them to be in the Pocky layer, but they are not there anymore, so it won't build. But there is a much simpler solution that is, don't use the Peta-Linux layer, just take from the Meta-Peta-Linux layer these 4 rules unmodified, which are the kernel module, the firmware, the user space library, and the OpenMax integration. Take them as is, and then take this bb-append file from the same layer, which is for GStreamer OMX, so it tweaks the OpenMax module of GStreamers to switch to the Xilinx fork, which is different from upstream, and apply some build flags to customize it for Xilinx. And then finally you can install GStreamer 10 OMX, and that's it. Nothing more. It builds and it works. You can write a pipeline that encodes H.265 or H.264 and so on. And well, I didn't test it extensively, but at very few tests it works fine. And that's it. So just to draw some conclusion, as you probably understood, this chip is very powerful and very flexible, but it's also very complex. And the same thing applies to software. Also, its software support is complex to set up, but if you know where to go and find the appropriate pieces, you can set it up. Also, Xilinx is providing their support currently mostly out of mainline, but they are working in mainline. At the moment, I think they're a bit slow in that, probably because they want to set up everything in their own branches first, but they are slowly moving, which is very good. And they are also putting an effort in using standard tools, which is promising for the future also. That's all. Hope that was not boring too much. Any questions? Yes? I'm sorry, can you speak louder? Okay. Okay, the question is if I consider for ATF loading using the fit image for U-boot, which is used in other platforms. The answer is no, I didn't consider it, because this approach is the one that has been implemented by other users of this platform or by maintainers of this platform, so it was already almost ready to do, but I think fit could make some improvement. SPL can road fit, I guess. Yeah. Okay. I don't. Yeah. What? Sorry? Okay. Yeah. Yeah. Right. So yeah, Rockchip is used in the fit image, probably others. I agree with you at first sight that this seems a better approach. I don't know if there are reasons it has been done in another way. Sorry. Mm-hmm. Okay. Yeah. I don't know why it hasn't been done that way. Sorry. Any more questions? Yep. With GPU Wayland support, I don't know. I don't know. I'm not using it. Sorry. Yes, that. Yeah, okay, so the thing is, using X11 does actually main copies of buffer if you use windowing, but in full screen it does not. Okay, right. But, actually, in fact, I used it only in full screen, but it didn't give any improvements in features over the FBDEF, so I stayed with the simpler FBDEF. So X11 for full screen seems like FBDEF to the user, so it's simpler. Okay, that's all. Thank you very much.